So this is Mr. Barron. I'm going to be doing problem number 83 from chapter 16. So problem number 83 is having you use data from Appendix D to calculate a hydroxide ion concentration and pH for each of the following solutions. I'm going to be doing A with you. On A, we're given a concentration of 0.10 molarity of sodium cyanide. Now, what's weird about this is that it's asking you to calculate the hydroxide ion concentration. So we're trying to figure out this. We don't know what it's equal to. And we're also trying to figure out what the pH is. Now, one of the keys to solving this problem is going to be looking up a value for Kb. And when you look in the back table, in the back of your book, it doesn't give you Kb values. Often you will only be given Ka values. And the way that you can convert between Ka and Kb is to know that Ka times Kb is equal to K sub w. K sub w is always 1 times 10 to the negative 14th. And if you're trying to figure out Kb, that's your unknown, and you're going to have to divide 1 times 10 to the negative 14th with the value that's in Appendix D in the back of your book. Okay? Now, what we're going to do is we have to write out the equation so that we can get an equilibrium expression. The compound we're working with is sodium cyanide. Now, sodium cyanide, one of the things I want you to remember is that sodium is always a spectator. You're never going to see sodium in an equation. That's because anything that's ever bonded to sodium is always aqueous. It doesn't do anything in this reaction at all. So you're starting off with cyanide ions. And obviously it's dissolved in water, so you're reacting it with water. And then that's in equilibrium with cyanide actually pulling off one of the hydrogens with the water and forming hydroxide. Now, if you're sort of wondering, like, where did this equation come from? How did Barron figure this out? Well, it goes back to how you know whether something's going to form a basic solution or whether something's going to form acidic or something's going to form neutral. This is actually really confusing in the book, but I have an easier way to figure it out for you. So sodium cyanide. Sodium, let's pair it up with a hydroxide, and let's pair up cyanide with hydrogen. Now what you want to do is label each of these as being either strong or weak as terms of being an acid or a base. Again, always pair up the cation with hydroxide, always pair up the anion with hydrogen. This is, without a doubt, a strong base. This is a weak acid. A strong base plus a weak acid will produce a basic solution. So that's why I was able to know that my equation would produce hydroxide as opposed to the opposite, which would produce hydrogen ions in the equilibrium. So it is an ice table. I say it's an ice table because they tell you how much you start with. And the amount that you start with in this problem is 0.10 molarity. So initially, you have 0.10 molarity. Now, there's something that's going to be tricky for you guys. And the thing that's tricky is I'm actually not going to pay attention and write any information down about water. Let me show you why. From this equation, we can write out an equilibrium expression for Kb because it's a base. K sub b is equal to products over the reactants. So it's going to be HCN OH minus over CN minus. That's the way I've written it out. Now, notice whenever you write a K sub A or a K sub B, you are never going to really have water in your equation. A classic one is K sub A. So in your equilibrium expression for acids, let me write this one out. And after I've written it out, you'll notice there's nothing in here about water at all. So I can ignore water in my equilibrium expression. That's the point of me writing this one out. So anyhow, ignore the water. Look at these two. These we know are starting off with 0, and this is going to be in equilibrium with these two. Now the change, we know that this is going to decrease by some value, which is x. And since it's a 1 to 1 to 1 ratio, you know these are going to go up by that same value. So it's going to be 0.10 molarity minus x. This is going to be x, and this is going to be x. This is what I can use for my equilibrium expression. Now, K sub b is something I can look up in the back of my book. They give you K sub A in the back of your book for HCN. And using that equation that I showed you on the top, if you look up the Ka in the back of the book, so having looked up the Ka value in the back of the book, the Ka for specifically HCN here, this compound right here is 4.9 times 10 to the negative 10. Now, using the equation that I showed up top, let me go up to that, this one right here, this is how I calculate K sub B. So what I've done is I've figured out K sub B. K sub B is equal to, sorry about the abrupt shift, but K sub B is equal to 2.04 times 10 to the negative fifth. Now, I'm going to go back to this. This is my equilibrium expression for K sub B. Now I'm going to substitute in these values for X into the concentrations. So K sub B is equal to X squared over 0.10 minus X. Now here's one of the really cool things that you can do. You can either do this, solve for X as a quadratic using your calculator, or because this value is really small, you can assume, and you have to write this down on your test, that it's 0. So if you assume that X in the bottom, just this one right here, is 0, what you get is 2.04 times 10 to the negative fifth equals X squared over 0.10. Now you just have to solve for X. When I solve for X, I got 1.4 times 10 to the negative third. So what's cool is that X gets plugged into here, here, and here. So X is 1.4 times 10 to the negative third. That tells me my hydroxide ion concentration. So this is OH. So I've already answered half of my question. Now I've got to figure out what the pH is. Unfortunately, I don't know the hydrogen ion concentration. I only know the hydroxide ion concentration. Since I only know the hydroxide ion concentration, the only thing I can calculate is not pH, it's pOH. The P, just always memorize, means negative log. Negative log of whatever this thing is. So if I have pKa, it's a negative log of Ka. If I have pH, it's a negative log of hydrogen ions. If it's pOH, it's negative log of hydroxide. So in this case, it's the negative log of 1.4 times 10 to the negative third. So I'm going to go ahead and do that on my calculator. And the math that I get for this, negative log of 1.4 times 10 to the negative third, I get a pH of 2.8, pOH, sorry, it's pOH of 2.5. Now comes our next favorite equation. pH plus pOH is always equal to 14. So to figure out the pH, it's 14 minus 2.85, and then I know my pH. And my pH in this problem is 11.15, which is the correct answer. Do we have any questions about that problem?